Alright, hell yes. We have physics, and what we're going to do is, you know what I mean? I read this problem once just about 5 minutes ago, and we're just gonna do it from scratch. So we have molten metal, and it splashes. So two droplets, at the same time, one flies that way, one flies that way. So they have an initial velocity. Kind of the overall thing about this whole situation is like, hey, we have an Earth underneath us, so we're going to have an acceleration downwards, and we're going to talk about that. But any velocity that we have sideways, there's no force on that. There's no forces sideways, and so whatever the velocity will be, it'll just be a constant. Okay, so what they want is they want to find an equation for the distance between these two, at any given point. So let's go back to how F equals ma works, because I mean that's the foundational principle of Newtonian mechanics, is that, hey, we've identified a mass, and now we want to, so that's this part, and now I put eyeballs on acceleration. Do we know anything about it? Sure, we know it has an initial velocity that way, and just by observation, what's going to happen? The droplet's going to go up and down. So in the y-axis, it's going to look like this, up and then down, you know what I mean, as it does its full arc to the ground. Okay, so I consider that, I mean, that's huge red flags that we have a change in velocity. Velocity was actually going up, and now it's going back down. So that is the definition. So once we observe that, we're like, okay, check mark, and we will have some acceleration. So now we want to know what the definition of acceleration is. It's going to be change. I'm just going to write it once, dv dt. You know what I mean? I've done a lot of videos where you just say, hey, just say what it is. It's the change in the velocity, change in time. So you can do caret v, caret dt. But anyway, so that's our equation. Other equations that we need to know is, what the hell is velocity? Well, that's change in position, change in time. Cool. So, and acceleration, now why is it 9.8? Well, yeah, so let's talk about this, because that's the hand-waving thing. Because a lot of problems will just be like, well, here's our mass, and guess what? mg. That's the weight of it. So they'll do w, the weight of it. The weight is a force, but there's a lot that gets lost there. You know what I mean? So let's just go back to this. We have F equals ma. So this is your observation side. But then this force side, this is your textbook side. You know what I mean? We have done statistical observations about the universe, and we have found, through equations that, you know what I mean? Hey, for this particle, we have like an Earth underneath us, and so we have a force of gravity that's gravitational constant, m1, m2, radius, and for this, radius 2 is just radius of the Earth. And I mean, mass of m2 is mass of the Earth, and this is radius of the Earth squared. Cool. So this is the force. You jam it into this side. So let's do that. So we're going to have g m1, mass of the Earth, radius of the Earth squared, is equal to the mass we're doing observation on. We're going to call that m1. m1 acceleration. Okay, hell yeah. So now, we have this relationship between, and then the masses. Well, I mean, this is F equals ma. This says, hey, this side is units of force. It's in units of newtons. This side is in units of newtons. But at the end of the day, what we want to do is figure out, the acceleration part. That's basically all you're trying to find out. So let's say this droplet, let's say you had a sphere in water, you know what I mean, and you have velocity, zero velocity here, but when you drop it in, hell yeah, you get some velocity. So you have identified a change of velocity. We're going to do the F equals ma. This is a good example. Okay, this is our mass. We've identified acceleration, so check mark. What do we know statistically, from the books about a sphere in water? Well, we know that there's a force of drag. So we have a force of drag this way. Cool. That slows it down in water. Okay, and then, but we can't forget about Kepler too. We also have a force of gravity. You know what I mean? So we also have a force of gravity. And so instead of doing mg for your problems, just write fg, and fg is g m1 m2 radius of the Earth squared. Cool. But then when you go to shove this in, you know what I mean? So I guess, and maybe I'm missing the two steps, but the mass of the Earth. So with a free falling object, or just any object, holy hell! But the acceleration is gme radius of the Earth squared, and this is literally 9.8. So that's basically where it comes from. But there you go. Now you're not hand waving, you know what I mean, where the 9.8 comes from. Now you're not hand waving what mg is. So now we have this acceleration that we're going to call g. You know what I mean? So if we say, hey, what's the force of gravity? Well, it's just mg. You know what I mean? And will this fly? Because we know the force of gravity is that Kepler side. So g m me radius of the Earth squared is equal to mg. Are these the same? Yes, because this is g. You know what I mean? So this is an identity. Yeah, it is fascinating. Even just when I come back to it, I'm sure I'm missing just one verbal step that makes it less confusing. But if we go to this sphere and water, well, cool. So now we have the F equals ma. We know, and we want to know the acceleration side. But the force side, we have to jam all these in. We have to add, you know what I mean? So we're going to have a frictional force up, Fd, and then minus force of gravity down is equal to mass times acceleration. Cool. And now we can just say, well, what the hell is the force of gravity? Instead of doing g m me radius of the Earth squared, which is literally just mg, then we can just now do it mg, you know what I mean? But I would do it as Kepler until you're just like, every time you get the force of gravity, use Kepler's equation until you're just like, no, I totally know that these three things add up to gravity, or the acceleration of gravity, and I know it's just mg. Now the force of drag, this is where things get really easy if you use Excel, because the force of drag is literally, they're saying it's just a constant times velocity. So we would go a constant times velocity is equal to mass times acceleration. Cool. Now what we want to find is acceleration. So to get an equation for that, we go acceleration is this side, kv minus mg divided by m. And now we're just money. We literally have an equation for acceleration, and that's when we go stick in our differential equation. We say acceleration by definition is dv dt. That's equal to kv mg m. And now I separate variables, so let's get the hell this dt over here. And literally, if I just wanted velocity as a function of time, it would just be kv mg m, and then we would have a t right here, you know what I mean, plus a constant. But this problem sucks because, you know what I mean, you already have velocity in here and you have velocity in there. So you have to like not do that and say you have dv dt is equal to kv mg m, and we didn't separate variables, you know what I mean, very well. So what we're going to do is bring this m upstairs, and now we can bring the dt over here, but now we have to bring this kv minus mg over here. So we're going to go kv minus mg. So now we have mdv with the kv minus mg, and now we can have just dt over here. So now we have integrate both sides. Well, hell yeah. Now this has a divide by v, and v to the negative 1, if you integrate that, goes to v to the negative 1 plus 1 divided by negative 1 plus 1. That's v to the 0. Okay, we're cool there, but now we're dividing by 0. No bueno, and you get a natural log, so it just becomes, you have to look it up in a book. Who cares? And then that's going to be your function of time. Okay, so anyway, so that's just kind of in a nutshell how the integration works, how you use F equals ma. That's why I like this sphere in water problem, because it does suck. And if you do look in the books, you can get an equation for, I apologize. This gives you an equation for, after all that, you are going to get an equation for velocity. All right, hell yeah. Well, I guess after all that, you're gonna get an equation for that has velocity and time, and then you have to rearrange the variables to get like velocity over here, and then hella, and then time over there. You know what I mean? And so, and then if you wanted to integrate again, then you would have to go dx dt is equal to all that jazz with time in it, and then yep. I don't know. I'm just going to take you through the first step of that one. I'll do a video on this. But so now we're just kind of ready to go. We understand the fundamentals of F equals ma. We get that for our problem. If we analyze this, well, hell yeah, we have an Earth underneath us, so we do have a force of gravity down. We don't have any force of gravity sideways. And so literally, neglecting air resistance, there is no forces sideways. So this is cool, because if we take F equals ma, we can take it in the y, and we can take F equals ma in the x. So for the y direction, hell yeah, we got to check on acceleration. But for the x direction, we have 0 acceleration. And so because if you had 0 acceleration in statics, like, you know, if you have a bridge or something, well, you also have acceleration as 0. And this means that your forces, if you do identify any forces, they have to balance. You know what I mean? So if we do have an mg in the y direction, well, it's got to balance with a normal force that's equal and opposite because we observe no acceleration. But that's not the case when something is just velocity sideways. There literally is there's no acceleration sideways. There's no forces sideways. And so we can take that droplet into outer space again. What I like to do is, chisel it, do the free body diagram by dotting what you want to chisel out of outer space. And if it was connected to something, hell yeah, you'll have adjoining forces, like some shear forces, some normal forces, and some moments. You know what I mean? That's going to be classic. But we chiseled it out. There's no material around it, so those are all 0. And now, you know, what forces do we have in the x direction? Nothing. And the way to think, you know, visually about that is like once you chisel this mass out of outer space, put it in like deep space away from every stars, and then if you do observe motion, like in this case, yeah, we do observe a velocity in the x direction. Well, cool. If that's the case and this thing is deep space, it's going to just continue with that velocity forever. So that's kind of a Newton's, I don't know if it's like the second law or, you know, it's one of those Newton laws. So that is the case. And it's just, I think that's remarkable and fascinating, because now you bring this droplet back to Earth. Well, even though you have a huge Earth underneath, there is no Earth out here sideways. You know, besides like a moon and a sun, you know what I mean? Those things are going to be negligible for this problem. So for our problem, and there's not a huge ass mountainside like next to it, that would also be negligible, you know, because it takes the mass of an Earth just to get any sort of appreciable acceleration. Or appreciable force, I should say. You know what I mean? That would cause acceleration. Okay, so hell yeah. So that there you go. So we have force is equal to mass times acceleration in the y. So now we can just say, hell yeah, negative mg is so we have an mg in that direction. That's our force. It's w. So you could say negative mg is may. You know what I mean? You could also say the weight force is equal to mass times the acceleration in the y. You know what I mean? So then from this equation, you'd be like, well, what the hell is acceleration in the y? Well, it's the weight divided by mass. Well, what's the hell is weight? It's mg divided by m. That's the same thing, and I'm sorry, it's negative mg. Weight is going to be in the negative. I'm going to say weight's going to be a positive quantity, but the arrow is negative. So there you go, and we have negative g. Our acceleration is negative g, and so now we can kind of start the problem. In the x direction, we have F equals max, and we just actually on this side, you know what I mean? Cool, we've observed that we don't have any acceleration, but this side, textbook, you know, on the left side, we have no observable forces. So actually this side is 0, and we have mass times acceleration in the x. We still have a mass, you know, with some number, but we must have to, this must be 0. Alright, so acceleration in the x is 0, and booyah. So now we can begin writing some equations. So we have acceleration in the y is negative 9.8. So now we'll go back and shove this equation in, make it into a differential. dv dt is equal to negative 9.8. Separate variables. We got dv is negative 9.8 dt. Integrate both sides, and we got v is negative 9.8 t plus a constant. What's the velocity when time is 0? So if we throw a 0 in t, we have to get the initial velocity. And we're just talking about the y direction. So this is dy, this is acceleration y, this is velocity in the y, dvy, velocity in the y. Cool, nice. And the time will just be a constant for both. We're taking time at 0 right here, so it'll be the same for both the x and the y direction. Okay, so, but the velocity in the y, well, we know if this is the angle the sun is shining, so this must be the sine component, so v initial sine theta initial. So also, this is the cosine component. So vx initial is v initial cosine theta initial. This is vy initial. This is vy at time is equal to 0, you know what I mean? So now, if this is 0, it has our constant. Our equation on this side is vi sine theta initial. So constant has to equal that. You know what I mean? So we could do over here constant vi sine theta initial if you want me to do all the steps. But this is equation for velocity in the y. Negative 9.8 t plus v initial sine theta initial. So at any given time, I can know what the velocity in the y is. You know what I mean? And so, like let's say this term was 10. You know what I mean? Or you know what I mean? I mean this term could be 9.8. And now you can see in 1 second our velocity is going to be 0. You know what I mean? So visually, you also want to look at an equation and be like, well, where's we know at 0, this is our initial velocity, but if these two equal each other, then we have velocity 0. That's the top of the arc, and now it's going to go the other way. So it would be like a second up, a second down. And if that's the case, you know what I mean, the max distance, if it's a second up and a second down, you know what I mean, we already kind of know the max distance these things could be away, because if we take the velocity in the x, that's a constant, and so velocity is meters per second. And then we know, like, hey, we know seconds. Do that. So now we just multiply those together to get meters. So we would have, and let's say this is just, 9.82. 9.8 velocity in the x, 9.8 velocity in the y. That's what we've started. I apologize. But yeah. The vertical component. Let's say the vertical component of the velocity is 9.8. And then the horizontal component is also 9.8. It's going to take 2 seconds, 1 second to go from max velocity to no velocity, then another second to get to that same velocity. So just from this equation, we would be able to tell, oh, it's 2 seconds, and now we would know a distance. Well, it's just this times 2. You know what I mean? So it would be 9.8 meters per second times 2. And 9.8 times 2, and we would get 19.6. So this one would be 19.6 meters away, and then the other one would also be 19.6 meters. So if that was the case, if the initial velocity in the y was, and this was a 45-degree angle, that would be 9.8 divided by cosine 45. So our velocity initial, if our velocity initial was 13.9 meters per second, but times 2.25, that thing's going 31 miles an hour, you know what I mean? So I don't know. I don't know what a droplet actually goes. Maybe it does go fast. But there you go. So could you have, 19.6 times 2 times 3.3? Nah. Could you have 2 splashes of droplets 120 feet away? Probably not. So this thing's going to be lower, but at least we have one representation of what's going on. Alright, hell yeah. So we're back, and so now we'll stick with this y direction, and then we'll say that the velocity, we're going to use this, is dy dt. So this is our velocity, and or dx dt, but it's also dy dt. I just have to keep that in mind. So we're going to take this velocity and we're going to say dy dt is equal to that, negative 9.8 t plus v initial sine theta initial. And now we separate variables, dt, dy over there. So now we get an equation for y is going to be, and holy, I sometimes mess up integration, but if we have t to the 1, we go t to the 1 plus 1 divided by 1 plus 1, so that's going to be t to the 2 divided by 2. You know what I mean? So now we got negative 4.9, that's 9.8 divided by 2, t squared plus v initial sine theta initial plus a constant, and we're sorry. See, even right here, this is t to the 0. You know what I mean? So you can always do that. Like even right here, this is t to the 0. So if you wanted to do your integration, it's t to the 0 plus 1 divided by 0 plus 1. So this component also is t to the 0. So we have a t right here, t to the 1, and now plus a constant. When time is 0, our position in the y is 0, because we have to, pick an origin, and here's y positive, here's x positive. Okay, so now, oh cool, and that just rings a bell. If this is x positive, this is x negative, and then we'll be able to have two different equations go in two different directions. Okay, so it's not going to have a constant, that's it. So here's our velocity in the y, and here's our equation for y. We can do the same thing for this acceleration. This is going to be dx dt is equal to 0. Separate variables. Now we have 0 dt. Integrate this. And if you think this is still t to the 0, it's still a function of time to the 0. You know what I mean? So when we integrate it, we're going to have t to the 0 plus 1 divided by 0 plus 1. And that's going to be t to the 1. Cool, but you're still multiplying by 0. That 0 doesn't go away. And so then for, oh, and I apologize, this would be dy. So acceleration is dv dt. So our equation for velocity in the x is just going to be the constant. You know what I mean? It's just going to be, after integration, then a constant. And so the constant is just the velocity in the x direction. So we have v initial cosine theta initial. And now that this reminds me, it's like, hey, this might be, I'm going to maybe call this 1, molten splash 1, and this is molten splash 2. So what we've been doing is equations for 1, and then the equation for 2, well, obviously the velocity will be in the opposite direction. If this is a positive v initial cosine theta initial in the positive x direction, then the other droplet will be in the other direction, just going the other way. All right, so can we just do position in one step? You know what I mean? Because velocity is dx dt, and so we're going to do, we would do dx dt, v initial cosine theta initial, separate variables, and then integrate. So now we have a position for x, and it's just going to be this v initial cosine theta initial with a t plus a constant. So when t is 0, so when t is 0, what's the x position? So we're going to call that 0. So cool, that's our equation. So now we have another two equations. Velocity in the y, velocity in the x, and this is for droplet 1. So by similarity, we know that the equation for droplet 2 in the y is the same, because it just goes up and down. It never goes below the horizontal. But we do know the velocity, well, let's do this one. So velocity in the x is going to be negative vi cosine initial theta. This is going to be for droplet 2. How about in the y direction? We just said that. The position is the same, so then the velocity in the y direction for the droplet's the same. So this is the only equation that's, and the position equation. So cool. So this is the position. The position is now, if we integrate this, is now negative vi cosine theta initial t. So this is the position of 2. All right, hell yeah. And so now the distance, at any given time, if we know if this is the equation for distance of the first particle, this is the equation for distance of the second particle. Let's just pick 1 second. At 1 second, this distance is VI cosine theta initial in meters away, and this one's negative VI cosine theta initial in meters away. So now the total distance will be, I guess the distance would be the change between those. So you could say if this is droplet 1 and this is droplet 2, this is droplet 1 and 2, you could say that the distance between, so we're just going to say d, and we want d as a function, of velocity initial and theta initial. Well, I think now we're getting to the point where it's just like easy and obvious, right? Well, it's just always just going to be, let's say, the distance and the positive distance. If you're just taking the overall distance and it's the absolute value. The distance is just the absolute value between them. But if we wanna not have to do an absolute value term, we'll just take the positive one. So we're going to take position 1 minus position 2. So we're going to go x1 minus x2, and then we get v initial cosine theta initial times time minus, and this is a negative, so it's minus a negative v initial cosine theta initial time. And cool, it's just going to be plus. So if we just add those two together, I'm just going to do that, then we just get 2 v initial cosine theta initial time. And so what the hell is they? So in terms of v initial and theta initial, find the distance between them as a function of time. Yeah, so there you go. So right now we have that. So we have a distance d as a function of, giving any, it's a function of v initial, theta initial, and time. So that's what we have, because we have 2 v initial cosine theta initial time. It is a function of all three of those things. You change any one of those variables and you get a great representation of time. But just in general, let's say we just say, hey, for my problem, I'm just going to say vi initial and theta initial is, I'm going to have to measure or those are going to be constants, for my problem. Now I do just have a distance as a function of time is 2 vi initial cosine theta initial time. And booyah. So I think that problem was pretty easy. Even though it was blue star, it's just like, that's why I tackle, it's like, well, let's throw the whole book at it, even though in the end it's just like, oh, that was a pretty good, easy representation. But when you do that second integration to get position, just know that it is the distance at any given. It's, you're starting at whatever your origin is, and for whatever time is, it's that distance. So at time t out here, that's that distance. And then at that same time t, for this other equation, it is going to be that distance. So here's distance 1 and here's distance 2. And d is going to be 1 plus 2. And it's going to be the absolute value of 1 plus 2. We just showed that if we did it, because this has negative distance, if we did it as the difference between them, hell yeah, we get a positive result. And cool. And I think I'm done with that one. So yeah, I don't know, leave a like if it is worthwhile going through, just all that initial setup, just when, at the end of the day, yeah, of course you're just going to go 9.8, t, and then 4.9 t squared plus, and then plus the velocity initial in the y, velocity initial in the yt, plus the position, which is usually 0. So now you have velocity and position function. You can do those just within, without all the writing. And let's do a check on reality, because we said that if we had a v initial of 9.8 divided by cosine 45 and a theta initial of 45, So I'm gonna store this as v initial. So we're gonna have 2 v initial cosine 45, and then we're gonna have 2 seconds. You know what I mean? And do we get the distance that we expect? All right, hell yeah. And so is that what we got initially? I kind of forget, but we're gonna go times 3.3. And then 129 meters. So yeah, so this is a full check on reality. I'm satisfied. But this answer is not in the back of the book. You know what I mean? So that's why it is just good to at least do a simple problem. You know what I mean? Hey, in 1 second, what's the, you know what I mean? And so we did a good job of like 1 second up, 1 second down, and we knew that if the velocity in the y was equal to 9.8, you know what I mean? Then at 1 second those would cancel, our velocity would be 0. In another second it would come down by symmetry, we could have also done that with this side. So let's do that right now. So you would factor out a t, so you'd go t times negative 4.9 t plus v initial sine theta initial, and then at what this says is that, hey, at time 0, hell yeah, we're right on the y-axis, you know, or the y-axis is 0. All right, so and then but if this side, you know, because you have two solutions here. When y is 0, you know what I mean? Hey, time is going to be 0, or this side is going to be 0. And so if we say alpha v sine 45, and so, you know, so we do a separate equation for this is 0, and we would get, you know, this is equal to 0. We'll bring that over there and divide this by 4.9. So we get v initial sine theta initial divided by 4.9, and that's going to be the time. And so we'll do that right now. V initial sine theta initial divided by 4.9, and sweet, that's 2 seconds, and that's also a check on reality. Okay, so I'm going to be done with this problem, you know what I mean? The other blue problem that I did, like, it literally took me, you know, 4 hours, you know, and 3 days just to kind of figure out what the continuity was. But this one seems very basic. But it's just like, yeah, you never know, you know, how hard a problem. For me, I can't tell how hard a problem is going to be. So, but anyway, we're done with this one. Thanks for joining me, and that's a video. Alright, hell yeah. We're going to do one more thing, is because, you know, we got an equation for distance as a function of time, but I was just, you know, every equation has a ceiling, you know what I mean? So if time goes to infinity, you know, obviously this thing would have to be on top of a huge mountain, and then, you know, nothing underneath it, and then it would hit the floor. So, but obviously, if this is on a floor surface, and it has this velocity, the second it hits the floor again, that's a limit on time. You know what I mean? So time can only be from 0 to whenever that happens. And I'm having problems with my camera right now, so I just did it once. But what we find is that we already figured out when that time's going to happen. You take this y equation, and you factor out the t. So at time 0, it's going to be on the y-axis. You know, y is 0, and then over here, it's going to be when this part of the equation. So we would have. Yeah, we can get this. It's when we have negative 4.9 t squared plus v initial sine theta initial t. This is our y equation. So we set that equal to 0. So then we factor out a t, and we go negative 4.9 t plus v initial sine theta t, just sine theta. We already factored out the t. And this says, hey, if it's a product, so since we do have a product, if either of these are 0, this becomes 0. So at time 0, we have 0, and then we have two separate equations. So now we have negative 4.9 t plus v initial sine theta initial is equal to 0. Cool, so we're going to bring this over to there just by doing equals and then doing that. So now these two are equal, and now we're going to divide by 4.9 to get t. So we have t is equal to v initial sine theta initial divided by 4.9. And this is a limit, and I did it in my calculator where, hey, alpha v sine 45 divided by 4.9, that is our 2 seconds, so we got to check there. And so now we can just... And then we know that this is 4.9 is acceleration divided by 2. So our time max is going to be 2 v initial sine theta initial divided by area. And then I just wrote those down. So heck yeah. So our distance, equation for distance is this. And then, you know, based on that card, you know, so you don't lose track of where I was. Now we have this time. For this equation, time can be between 0 and it can be as, this would be the max, you know what I mean? And then that's just a check on any equation. You know, you got to do a check on reality of, like, the first check is like, well, when is it useful? Is this useful when time is -1? No, that's nonsensical. So so there you go. So now we have a representation, a true representation of the distance as a function of time on a horizontal surface. You know what I mean? This will change if the molten splashes from a table and then back onto the ground. You would say, hey, this if this is our datum, like y x, then this y would be like negative, you know, let's say negative 2 meters, and then you would put this equation. So you'd go back to this equation and put -2, and then solve where t is equal to 0 at both those locations. And then it's a true quadratic. You'd have to use the quadratic equation to figure out both t's, and there you go. Oh, that's wigging me out, because in the table example that I just showed, if you're setting time is equal to 0, x is equal to 0, y is equal to 0, well, at t is equal to 0, this has to be 0. So your quadratic, I don't know if that's an official answer, officially true for the quadratic. I'd have to check that, because it seems like if y is equal to 0 when t is equal to 0, you know, you would just factor it through. So yeah, this is probably wrong. Anyway, I'm going to leave it at that, and hell yeah. Alright, so we're going to actually do one more thing with this problem, just because, hey, if this was on a table, like, I just wasn't solid in my explanation of, like, you know what I mean, we kind of knew what's going on. So I am going to say this is x positive, and this is y positive, and then here's the origin, 0, 0. And so what we want to know is, you know, the time frame if we do have this at some sort of height. You know what I mean? So actually, well, let's do this now. So our equation will be like, hey, what's the max? Get an equation for this distance. That'll be the same, but then we're going to introduce this height component, and we want to know how that changes the equations. So we're going to have acceleration is negative 9.8. We're going to have velocity is negative 9.8 plus, you know, the initial velocity in the y. And that's going to be v initial sine theta initial. Oh, and there's a t right here. And then we're going to have position is going to be negative 9.8 divided by 2 t squared plus v initial sine theta initial t. But now, and I apologize, this is just y. So when time is 0, y is going to be 0. Okay, so yeah, this equation did not change. That was fascinating. It was just the fact that so at time is equal to 0, this equation says that y is 0. That was the trip up. That's where I was getting tripped up. But if we say what's the time when height is, you know what I mean? And I don't know if 2 meters, that would be like a really tall table. It would be like 6 feet off the ground. So let's just do height is 1.5 meters. So still pretty tall table, but we're going to have sparks coming off 1.5 meters. So then we would do 1.5 is equal to negative 4.9 t squared plus v initial sine theta initial t, and then we'd have to use the quadratic equation. So let's do that. Let's get this over here. So we're going to go 0 is equal to negative 4.9, and let's use the quadratic equation. Let's do this in terms of just acceleration. So y is height. So we're going to say, hey, when 0 is equal to negative a divided by 2 t squared plus, and then we're just going to encapsulate this. We're just going to say vx. You know what I mean? No, I'm sorry, vy. This is the velocity in the y direction. So we're just going to say vy of t, and then we have minus h. So there you go. So this is the equation that we would solve for the quadratic. And let's walk through there. I love, instead of just going to the quadratic equation, and what is it? You know what I mean? X is, because let's say you don't remember it. You know what I mean? And even if you did remember it, maybe you got it wrong. I think it's negative b. You know what I mean? Because and then think about this. This is in meters. You know what I mean? This has to be in meters. Then we have plus or minus the square root. So everything under here has to be like meters squared. So the first thing we come across is b squared. And I know that there's not a negative in front of b squared. I don't know. It just because if there was a negative in front of b squared, this thing would have to be in parentheses. And I just know that it's never written in parentheses, so we just have b squared, but I do know this is minus 4ac. Cool, and then it's just all divided by 2a. So how do you derive that? I love deriving it, so we're going to say that you do 0, and then you just do a common polynomial. So we say a x squared plus bx plus c. So now we have a common polynomial that's equal to 0. And so to get it in a form of like, so we're trying to do this, x plus or minus something, x plus or minus something, you know what I mean? And then, hey, that's x plus or minus something squared, and then that might be equal to something over here, and then we can take the, we can take the square root of this and take the square root of that, and then we'll have x plus something is equal to the square root of something, and then we can just minus that little thing. So we'll have x is equal to the square root of something minus that. So that's kind of the general gist of what you're trying to do. You're trying to take this and get it into x something, and these two things are the same. When you do that, there is no constant out here in front of x, so that's just a good reminder that the first step is divide everything by a. And we have 0 over here, so 0 divided by a is still 0. So we're going to have 0 is equal, and then they usually flip this around. They usually do this is equal to 0, you know what I mean? And then visually it just kind of, that's what the textbooks do. You wouldn't have to do that, but visually it's nicer. So we're going to go x squared plus b divided by a, x plus c divided by a. That's all we did, is equal to 0. Okay, so now the other thing about this is like you have an x squared term and then this term. I guess at the end of the day, you just have to remember to get this constant over there. Just get it out of there. It's not going to help you find this, this double x something times x something. So we're just going to do that. That's the next step. X squared plus b over ax is equal to negative ca. Okay, so now that we did that, now this side, now we just have an x and an x. We're not just going to factor out an x and go x plus b over a. You know what I mean? We're not going to do that. But could we? I mean, is that another way to? No. I don't think so. No, because that would be interesting. Holy Toledo. Even just doing this, you're just like, well, I mean, that's the cool thing about math. As long as you follow the axioms and don't make a mistake. But no, that won't help us because that's equal to negative ca. Only when this product is equal to 0, then you can say that if either one of these things is 0, then that is 0. So this could be whatever, but that's 0, that's 0. But what we just said right there is x is equal to x plus b over a is equal to a constant. And so, I mean, sky's the limit. There is, both those things could be anything, okay, to get that constant. If one is something, the other thing can obviously be anything. But when it's equal to 0, if one of them is 0, the other thing can be absolutely anything, but it's still 0. I mean, but if you have something equal to one thing, this could be anything, but this has to be precisely another thing to get that constant. Okay, so so what we're trying to do is get in the form of that. So what we do is we just do x and x. And what do we know about this? You know what I mean? Let's say we had x plus 1. You know what I mean? That would be an easy one to do. We can learn something about it. Well, we're going to go, and the way that I like to do this is, hey, this is just x squared plus 1 squared plus 2x. You know what I mean? And so I think that's the fast way. Typically what you would do is you would go x squared plus 1x plus 1x plus 1 squared. You know what I mean? And then you would do that. And then you have kind of this term, is kind of a product of, it's like, there's two of them. There's two identical terms there, so they go to 2x. And so, so whatever this term, so this is that step where it's just like, well, whatever this term needs to be, what you're trying to do is it has to look like that term. So if we're saying if our form is like x plus, then we'll just do this, b divided by 2a. So 1/2 ba. That's kind of what you're doing. 1/2 b over a. Plus 1/2 b divided by a. So now when you do this, and if you do it this way first, just do like x squared plus b over 2a squared plus, and then this next thing is just going to be this times this times 2. So we would have x b over 2a times 2. And that's kind of the form that I like to do. It's something different, but let's do it, kind of like normal. You would do x squared, kind of FOIL this through, and then you would have plus. All right, then you would have 1/2 bax. You know what I mean? And then you would do this FOIL through, so you'd have another one, 1/2 bax, and then you would square these two, so you'd have plus. B over 2a squared, and this is, oh, sorry, there's that 1/2 right there. Okay, so hell yeah. So then when you combine these two terms, it's 1/2 plus 1/2. You get bax. Cool. So now you have something that says x squared plus bax plus, now you have this term b 2a all squared. So this is the term that you're needing. You know what I mean? So right here, at this stage, you need to add something to both sides of the equation. And that's the thing that you're adding. You know what I mean? And, I'm doing every step, but even when I do it, I skip all the explanatory steps and I just do it. But I do this just to make sure. It's a good check on reality, and it's a fun one to do. Okay, so now we're going to get x squared plus bax plus this b over 2a squared is equal to negative ca plus b over 2a squared. So we just added that term on both sides. Now you can definitely FOIL this one. X plus, and this term right here is going to be that. It's going to be b divided by 2a. Cool. X plus b divided by 2a. Because now, if we have the x squared, we have that term squared, and then we have two of these. X times b2a, we have two of those, so that's going to be xba. And that's the way that's why now I like to just say, hey, if I'm squaring something that's totally identical, I'm going to have, I can just do this real fast. It's x squared plus b over 2a squared. And now I can worry about that kind of funky one of just being like, okay, it's these two, but twice them, so it's ba times x. Cool. And then I'm a check on reality, and it's identical to that. So now what this says, the next step is to do x plus b over 2a squared is equal to negative ca plus b over 2a. This is still all squared. But right now we can take the square root of both sides, and we can just get this x plus b2a. and that's going to be the square root of negative CA plus B over 2A squared. And now to get x, we just got to subtract this B 2A. So we're going to have negative CA plus B over 2A all squared, square root that, minus B over 2A. And then I usually just stop right there because it gives me a check on reality that I can compare to that one. How they kind of factor, how they get it to look like that and getting this 2A outside, it's always a good one to do. You know, but you don't have to. You're done. You're done at this point. The next part is like circus trickery of like, well, you would have to get, you have to see that this B over 2A squared is B squared divided by 2 squared A squared. That's a form to do it, or you can just say B squared divided by 4A squared. So now you have negative C, and then this is B squared divided by 4A squared. Well, so this term right here is 4A squared on the bottom, and you want that term to look like 4A squared on the bottom. So you would multiply this by 4A. That means you have to multiply the top by 4A, because when I multiply by 4A divided by 4A, it's like multiplying by 1, and it doesn't change the relationship. So now you get negative 4A, so you get negative C 4A on top divided by 4A squared on bottom, plus this B squared divided by 4A squared. So now you have that. And what well, we have to still have to do one step. Since you have this on the bottom, you can say that we just have 4A squared on the bottom, and then the top is going to be negative C 4A plus B squared. You know what I mean? And you can obviously take that one over there, take this one over there, and negative C4A is the same thing as negative 4AC. So this becomes B squared minus 4AC divided by 4A squared. And we still have to take the square root of it, but this is where you definitely want to use that trick of like, hey, anytime I'm taking the square root or the exponent of like a fraction, you know what I mean, you can always do the square root of the top and then the square root of the bottom. And then once you did that, like let's say even this, you could take the square root of even the individual terms. Since you have a plus and minus here, you can't do that trick. But because this is a product, this is also the square root of 4 and then the square root of A squared. Sometimes visually, it just makes the math make a lot more sense when you do stuff like that. So now you can easily see square root of 4 is 2, square root of A squared is A. So now we have that 2A outside of the square root, and then that's on top. So this whole thing on that side becomes the square root of B squared minus 4AC divided by 2A. And then this side is still negative B divided by 2A, and now you can see that we can use that same property. We can say that x is just 2a, and then everything upstairs is b squared minus 4ac minus b. And so see how it's all over 2a. And then just the way that it's written, and then anytime you do a square root, the second you do this step where you actually take the square root of both sides, this is where you get that plus 1 minus 1. It's because you have imaginary roots. You know, watch a YouTube video on that. I'm not the one to explain, you know, in very like I do in with an over explanation of you know, kind of why you get that kind of imaginary setup. All right, hell yeah. So, but there you go. So you got that plus minus through all of these square roots, and then just the answer in the back of the book. They just do the negative b first. So you get negative b plus or minus the square root of b squared minus 4ac divided by 2a. But all the other forms in between are still just, you know, they're okay to do. Okay, so now we're gonna rewrite our, so we're going to, velocity in the y is negative 9.8 t plus v initial sine theta initial, and then our y is going to be negative 4.9 t squared plus v initial sine theta initial t. And what we did was say that this is, we're going to say that y is is a divided by 2 t squared plus vxt, and then for our scenario where y is equal to h, and so here's h. This is a bummer because h has to be, h is going to be a negative. I don't know representative wise h, if it is 125 meters. When it's in here, it has to be a negative. So I don't know how I would represent that 100%, but yeah. So it's when y is negative 0.5 meters, we have a squared t squared plus vxt. So I made a mistake on that. You know what I mean? Because this is the y positive. This is the y negative. H is negative 1.5. So let's do that where it's negative, and then so we pop it over here, it's going to be a positive. Okay, and again, acceleration is a negative 9.8. Yeah, that's just, I don't know how to write this. It's like, hey, is that negative h? And then you put it in. But anyway, I think we can work that out. So we're gonna have 0 is equal to a divided by 2 t squared plus vxt, and then this is going to be yeah, I guess I'm just, oh man, I'm gonna say h is negative 1.5. So, you know, when y is equal to h, so h, alright, heck yeah, so h is negative 1.5 meters, and then, you know, we'll just throw it in as y. So right here we have, so we would have y is equal to, so when we bring the y over here, we just have negative y. So cool, so now we have something in the form of a squared x squared plus vxx, you know, minus y. So here is our quadratic, you know, I mean, this is my a term, this is my b term, and this is my c term. So a term is a divided by 2, b term is vx, and c term is negative y. So if I just wanted to use the classic of x is equal to negative b plus or minus the square root of b squared minus 4ac divided by 2a, then I could just throw those terms in there. So I know that x is, so b, so this would be a negative vx plus or minus the square root of vx squared minus 4 times a. Well, a is negative, so we got 4 times oh yeah. So my, oh sorry, holy Toledo. Here's my a. My a term is a divided by 2. So we're gonna go 4 a divided by 2 times c, which is negative y. Cool. So now we have that, and then we're going to divide by 2 a. So that's acceleration is a, but that's different than the a that's in the quadratic equation. So a is a divided by 2 times 2 is just left with acceleration. So now we're all done using the ABC over here. We've already substituted them. A in here is acceleration, Vx, and then y. So we can simplify this. How would we do that? We would say that this is 2. I mean, the negatives go to a positive, so it's plus 2ay. So we have plus 2ay right here. And then, so cool. So we're good to go. So we have x is equal to negative vx plus or minus the square root of vx squared. plus 2ay divided by a. Nice. All right, so we just do it. So our x is equal to in our Vx, in our problem, Vx is velocity initial cosine theta initial. So we're going to have negative velocity initial cosine theta initial plus or minus the square root of velocity initial squared cosine theta initial squared plus 2a plus 2ah. I'm going to say y is h. Cool. And divided by the acceleration of gravity. Okay, so now we have, and then this whole thing was solving this quadratic. And I know this is like a hella complicated way to do it, because if you just had numbers, you would just throw in the numbers, you know what I mean, and then get a number. And the number we're getting, I changed this variable. We have t squared plus t. Well, obviously x in this case is t, you know what I mean. So you can use that. So this is synonymous with t, and so we have the time. We have two different times. You know, that would make sense. So we do kind of have to throw, you know, we have to have some sort of check on reality. So I'm going to say my initial velocity. Yeah, we'll do that. We'll do that initial velocity. We already have it in our calculator, 13.89, and then times cosine of 45. That makes it 9.8. So hell yeah. So this initial velocity is going to be negative 9.8 plus or minus the square root of 13 point, basically 9. This is Vx squared, so this is just 9.8 squared plus 2 times 9.8. And then the acceleration is negative 9.8 in that one. Plus 2 times negative 9.8 times negative 1.5. Alright, heck yeah, divided by negative 9.8. So let's do that one more time. Time is equal to, we have negative velocity of the in the x. So that's going to be negative 9.8 plus or minus. Now we have that velocity in the x squared. So that's going to be 9.8 squared plus 2 times the acceleration is negative 9.8, and then the height is negative 1.5. Okay, hell yeah. Just a little bit cleaner, but and then divide by the acceleration is negative 9.8. Okay, so now we can do that in our calculator. We got negative 9.8 plus the square root 9.8 squared plus 2 times 9.8 times 1.5. I just got rid of the minus signs. Alright, so that's that. We have to divide everything by negative 9.8. Divide by 9.8. Cool, so we get this as a time of 0.14 seconds. And if we do the negative root, so we're going to go minus, and that gives us a minus time. So that's nonsensical, and that won't work. So if we have something, yeah, that's kind of interesting. I'm surprised that that time is, it feels like this time is wrong, and it should be wrong, because we already said that if we have initial velocity of 9.8, it'll go up and down, and t is equal to 2 seconds. And so what we did is say that, that's fascinating. That's where you're going to run into issues. I mean, we did the whole quadratic equation, and I absolutely hate the quadratic equation just because you might throw in, you know, you do have a negative here, and then you have to make sure if this is negative here, that it's portrayed in the equation. You know what I mean? So sometimes, you know, if I'll just change that to negative just to see if it if I made like a weird error there. So yeah, so let's go back and here's our equation for y. Our equation for y is negative 4.9 t squared plus v initial cosine theta initial times time, and we want to evaluate when y is negative 1.5. So it's going to be 0 is equal to negative 4.9 t squared plus v initial cosine theta initial time, and then this would be plus 1.5. Because if I want to evaluate when y is negative 1.5, we bring it over here, it's a positive 1.5. And so that's where this term is, yeah, we're inputting a negative y, but it's minus negative y. We get 1.5. We get 1.5. Yeah, and c is negative y, and y is negative 1.5. So when we have c, you know, we inputted a negative y into c, and that was, oh, see, yeah, this is probably where my, well, no, I guess not. So we have a negative, oh, yeah, let's see. Is this where my error is? Because if we did this one, we would have negative 4 times negative 9.8 divided by 2 times negative 1.5. You know what I mean? So this would be a positive. All right, so yeah, this would be a positive, and then these two things would be a positive, and then we would just have a positive answer. So when we go in to do this in the end, yeah, we just have you know, a total positive value up there, which we do. So man, so that's so fascinating. So let's solve this. You know what I mean? So we would have 0 is negative 4.9 t squared. This v initial cosine theta is I thought it was just 9.8 cosine 45. Yeah, so this is 9.8. So we have plus 9.8 t plus 1.5. You know what I mean? And so I'm just going to do a quick graph, negative 4.9, because this is another way to just make sure you have a check on reality, and it's probably faster. And I know my t, well, you'll just graph it like normal. So zoom 6, and oh, whoa, zoom out. Oh, what up? Oh, I didn't do the squared. Holy Toledo. Okay, zoom 6. Okay, heck yeah. And we get a root that's just a little bit more than 2 seconds. That's what we're expecting. We're expecting 2 plus seconds. So it's just a real bummer that my quadratic equation, you know what I mean? I hate the quadratic equation. It's just too many places to make errors. So now the value that we're trying to get on the quadratic equation is 2.14. So now this is the form that we do. So A is negative 9.8 divided by 2. So we have that. And then and that's exactly what this was. This was, so A is negative 9.8, and this is negative 9.8 divided by 2. This is going to be v initial cosine theta, which is Vx, and that's going to be a positive. So B is v initial cosine theta initial. And then in this, though, but our C term is just, yeah, and our C term is negative y if y is equal to, if h is equal to negative 1.5, That's going to be our y. Y is equal to h, and this has to be a negative y. So we were good there, even though it's just a little bit confusing. Because when we throw in negative 1.5, we get that positive. And and then the quadratic is negative b plus or minus the square root of b squared. Snikes. You know what I mean? Well, this is minus 4ac. So we have minus well, no, I mean, yeah, this minus 4ac term always gets me. So we got minus 4. A is a divided by 2. C is negative y. So then we're going to have plus 2ay. And there you go. And y is h, which is negative 1.5. You know, so yes, so it's still plus 2ay. And we should be good there. And then when we divide by 2a, that's 2 times that, so it's just a, it's negative 9.8. So, holy Toledo, I guess let's just do this, negative 9.8 plus, but that's just a nice thing to have, like, multiple ways. I'm going to do the parentheses first because we have to divide all that by negative 9.8. Negative 9.8 plus the square root 9.8 squared plus 2 times negative 9.8 times negative 1.5. I think maybe I just missed a minus sign in these. That's what I'm hoping. Divided by negative 9.8, and we get that's going to be the negative root, and then so we're going to throw in a negative sign. Hell yeah! So I think in my calculations, it's fascinating to figure out. Yeah, so right here I didn't have any negative sign. I just said negative 2. So that's where I messed up. That one I had a positive. But then I got that as my negative root because I didn't divide by a negative 9.8. I didn't do that. So it's just fascinating. There's a lot that can go wrong here. So at the end of the day, what I just kind of proved is like, hey, you get an equation that says, you know, you get this equation, and then just graph it, you know, and then you're just good to go. And then you can get your answer. So there you go. The time was 2.14 seconds. And the equation for time was the negative root. So we're going to have the negative root. I'm going to pull that up one more time. Perfect. So now, because what I wanted to do was, you know, and we have the acceleration and the x is 0, so we have we just have velocity is the constant, velocity initial in the x direction. So v is v initial cosine theta initial. Give some more time. Alright, so, and then if you integrate this, the position is going to be v initial cosine theta initial t. So this is the distance for this droplet, and we just showed that the other, so this is for droplet 1, the position for droplet 2, you know, based on symmetry, is negative v initial cosine theta initial t. Going back to the actual d between these two droplets, we can say, well, if we want, it should be the absolute value. We could do absolute value of x1 plus absolute value of x2 to get that distance. But we know that this one's always going to be negative, so we can just take this one minus. So d is x1 minus x2. So minusing a minus is adding them together, and then we get d is equal to 2 v initial cosine theta initial times time, and that's our equation as a function of time. And we just showed from, but we know time has to be, you know, time can be 0, and time cannot be negative 1, and time has a max. So t, like t max is equal to this quadratic equation. So now we can actually kind of simplify this. We have we just have a, so we have the acceleration minus the square root, acceleration squared. I'm just going to go plus 2, 2a, 2 times the acceleration, times our y, or our height, I should say height, and then divided by the acceleration. So here you go. I'm going to write that again. T max is equal to acceleration, and I guess if we want to get technical, in physics books we already talked about that. Acceleration is gravity, so we're going to see T max is equal to g. Trying to clean this up. T max is equal to g minus the square root of g squared plus 2gh divided by g. There's even a way to clean this up. You know what I mean? So we're good to go. And then t has to be less than or equal to t max and greater than or equal to 0. So there's our equation for d. Hasn't changed. But then here is our limit on time, and that's definitely what I wanted to show. And I apologize for, just, over-explaining to where you're just like, well, we got lost in the weeds. But no, my videos are brilliant because you're going to make all those same errors. Anytime you use the I hate the quadratic equation. You might as well just graph it, because your equation is so simple right here. You cannot mess up graphing that whatsoever. And the second you graph it, you have a visual representation. That's why I could have captured my error, and let's talk about that. I could have captured my error because we just solved the quadratic equation in a different form. I said we could get it right to here where x is equal, or t is equal to plus or minus the square root negative c divided by a plus b divided by a all squared, square root of that, minus b over 2a. This was the first place that the quadratic equation would give you an answer. And so again, if a is a divided by 2, b is v initial cosine theta initial, and then c is going to be c is just going to be h, and that is going to be a negative number. Okay, hell yeah. So now we have time is equal to plus or minus the square root of negative h divided by a divided by 2. So that's just going to be 2. And let's do this. This is g. Acceleration is g divided by 2. Hell yeah. So now that'll really make it a lot better. Plus v initial cosine theta initial divided by 2 times a. So even here I can simplify. 2a is just always going to be g. So hell yeah, g. This is all squared. Square root of that minus v initial cosine theta initial divided by g. And if we do this one, we'll have two different roots. I think we'll do the negative root first, but we have 2 times negative 1.5 divided by negative 9.8. Plus alpha v cosine 45. That's just 9.8, so we can write that in as this is 9.8 divided by 9.8. Oh, cool! This is just 1. So I'm not even going to square it. And then minus 9.8 divided by 9.8. That's 1. Minus 1. Cool. And we get. Well, obviously we need the positive root on this one. Oh, what up? Oh, I'm off by a factor. I'm off by a negative sign. So the negative root is what we want, but yeah, it's like why didn't this work out? You know what I mean? So hopefully. Oh, I see. Holy Toledo. Same thing. I mean, we tried to make this problem simpler to make this 9.8, but obviously this is 9.8 divided by -1. Oh, no, and that just comes out in the wash as a positive because we're squaring it. This was 2h divided by 9.8. Yep. Oh, this thing is negative. Sorry. See, even that. This is why I hate the quadratic equation. There's so many negatives that overlap. It's an absolute nightmare. Absolutely hate it. So we have negative 2 times negative 1.5 divided by negative 9.8 plus positive 9.8 divided by negative 9.8. But that's going to be squared. You know what I mean? If we're going to do this legit. So now that's squared, and now that's all under the square root minus 9.8 divided by negative 9.8. You know what I mean? So there you go. And yeah, obviously we need the positive root. That's what we just showed from the actual quadratic equation from this one. We need the positive root. And so, yeah, we're going to do this positive. I mean, there you go. Holy Toledo. So this is still messing up. Negative 2 times 1.5 divided by negative 9.8 plus 9.8 divided by negative 9.8 squared. And then outside the square root, we have negative, I'm going to do this in parentheses, positive 9.8 divided by negative 9.8. And, oh man, this sucks. Yeah, this is brutal. And so I'm thinking that maybe I didn't write it down right. You know what I mean? So we have negative c divided by a plus b divided by 2a squared. And it's the positive or minus square root of that. And then minus b divided by 2a. And that's going to be x. Alright, so, and I'm just, in my calculator, I'm going to say a is g divided by 2. So we're going to have 9.8 divided by 2 minus, inverse that. We're going to store that as a. We're going to do alpha v cosine 45, stored as alpha b. And then the height, negative 1.5, stored as alpha c. And so, and now we're just going to do negative b plus the square root of alpha b squared minus 4ac, all divided by the square root. I mean, all divided by 2a. All divided by 2a. Whoa. Yeah, what a nightmare. You know what I mean? So this is a is alpha a negative, okay, alpha b is 9.8 and the alpha c is 1.5. And this is negative b plus or minus b squared minus 4ac divided by 2. Oh, whoa. I apologize. This is a huge hiccup. I've been, this has to be divided by a. If you're going to write it like this, it's divided by 2, divided by a, else you have to put it in parentheses. I'm going to run into a lot of errors that way because I have been enjoying just being like, hey, this is divided by 2, but then I do have to do divided by a if I'm going to do divided by 2a. So there you go. Divided by 2a is just like that. Or divided by 2 divided by a. That's the same thing as dividing by 2a. Cool. So now I'll use this one because it's visually more representative. Do the positive. Well, I'm still getting a terrible answer. So here is negative 4.9x squared plus 9.8 plus 1.5. Oh, see, yeah, holy Toledo. So I think there was such a so when we threw in y on this side, this equation says h is equal to negative 4.9 time at h squared plus v initial cosine theta initial time at h. So the time when this particle reaches the ground at this h, you know what I mean, that and h is negative 1.5, that's going to be the time that happens. But our quadratic equation is going to be 0, negative 4.9 t squared plus v initial cosine theta initial plus 1.5. So now if h is equal to negative 1.5, this is minus this is going to be minus h over here. You know what I mean? So this has to be positive 1.5. So if we in our c c is minus h. If h we're saying is negative 1.5, and I know that's like the hugest. Like I have a really hard time keeping tracks of negatives. Sometimes I just solve things with absolute values and be like, because they just make so much more sense. So yes, when we do the quadratic, this value is going to be negative h, where h is negative 1.5. Alright, so, you know what I mean, holy Toledo. So now when we throw in our quadratic for this, our c value has to be, so if our h, so if negative 1.5 stored as alpha h is that, this term is minus h. Our c term is minus h. So in our calculator, minus alpha h is 1.5, stored as c. That is our c term for our quadratic. That is where I got the answer messed up. And so now we can go back to our quadratic equation, and that's going to be the positive root. We need the negative root, negative, and we get 2.14. Now if I go back to the equation that I wanted to use, which was this one, because this is the, and I'll write it again. So this is the first time we can actually say x is equal to plus or minus the square root of negative c divided by a plus b over 2a squared, and then minus b over 2a. And this can be a check on the actual quadratic equation. Just because, I mean, it's a check because you're just throwing in different values in different orders. I mean, you're using the same a, b, c. It's going to get you the same two x values, but it's just different, so you can uncover errors that you might actually, I make a lot of errors. I'm going to do the negative root first, negative square root of negative alpha c divided by alpha a plus alpha b divided by, see, even right here, if I wanted to do divide by 2, I got to go then divide by alpha a. If I wanted to do that, then parentheses squared. This is representative of divided by 2a. So I'm confident with that. Negative alpha b, same thing, divided by 2 divided by alpha a. If I wanted to do it that way. And then, so the negative root wasn't the one I wanted. I wanted the positive root. Whoops. And I get 2.14. And in this one, this is fascinating. That in one scenario, I always thought like, well, does it matter what the negative or positive, or did I just make another error where, in this way, I have to take the negative root, I have to take the positive root to get that 2.14. But using the quadratic equation in this form, I had to get it was the negative root. So in this case, it was the positive root that gave me the answer. In this case, it was the negative root. And for the life of me, I can't see why that. I feel like there is an error there, but I don't know. You know what I mean? I hate the quadratic equation. I like deriving it, but I just realized there's so many places to get into errors. But anytime I can do a quadratic and use this, I'm going to do these in videos. You might just have to skip ahead because it is good practice for me not to lose negative signs, to be very specific about what my letters are, because I wasn't in this one. You know, h is negative 1.5. Y, that means y is negative 1.5. But then when I do the quadratic, my c value is negative y. My c value is negative h. Either one of those would have given me the right answer. And that would be c is negative 1.5. And c is negative 1.5 for, you know, both those. It's just positive. So positive 1.5. All right, holy Toledo. So, but there you go. So, oh, I guess we still, you know, had I done everything right and not made mistakes, we would have gotten to this point. And I just need to do a check on reality for this one. So we got negative 9.8 stored as alpha g. So we're going to do this. Alpha g minus the square root alpha g squared plus 2 alpha g alpha h. Hopefully that h is what we want. And then all divided by h. All divided by g. Excuse me. Yeah, and so that is the max time. Now I want to do one more thing because it's just fascinating. I like the idea of trying to simplify stuff. So I'm going to write the T max is g minus the square root g squared plus 2gh, all divided by g. Now, this is the same thing. I'm going to do this first. G divided by g minus the square root g squared plus 2gh, all divided by g. And now this is the same thing as, this is cool. I wasn't thinking about doing it this way, but this is the same thing as saying the square root of g squared plus 2gh, the square root of it, is also the same thing as saying the square root of g squared. Cool. Now that these both have square roots, I can combine them under one square root sign. And then I'm just going to make that 1. So we've already simplified this as 1 minus the square root g squared plus 2gh divided by g squared. And then that's all under the square root. Well, cool. Now I can do these two terms separately. So that's going to be 1 minus, this is going to be g squared divided by g squared plus 2gh divided by g squared. Hell yeah. So now I can see that this is 1. So I'm going to have 1 minus the square root of 1 plus 2h divided by g. Hell yeah. And that's T max. So that's the simplest way to get T max. And let's just see if it works. 1 minus the square root of 1 plus 2 alpha h divided by alpha g. And of course it doesn't work. Alpha h is negative 1.5. Whoa, where would we go wrong? Because this one worked. Unless I typed in this one. G minus g squared plus 2gh. All divided by g. 2.14. This is g divided by g. And this is that divided by that. This is going to be 1 right here. But minus. And this squared works. It's a positive with the 2gh. So we have 1. So it's 1 minus 1 plus. And then we just have 2h divided by g. 2h divided by g. So this is 1 minus the square root. 1 plus 2h divided by g. And I think there's nothing wrong with that. Is it just the fact that we have something funny with the... Man, this is so interesting. So I guess anytime you have a square root, you just have to do the... I don't know enough about square roots. Like, I bow down to people who do. But now I'm never going to do a square root where this is not just positive or negative and you figure it out. You have to find it. Because now this was saying that this wasn't right. So, positive or negative, positive or negative. Positive, negative, positive, negative, positive, negative. But it wasn't the negative root that worked. It was the positive one here. So I can say T max is equal to 1 plus the square root of 1 plus TH divided by G. But yeah, again, using the negative root here is the same thing as the positive root here. And I think I just answered my own question, that I did not make a mistake on the quadratic equation. It's just that anytime you have a square root, this thing can flip-flop. It's just evident that that thing can flip-flop depending on the structure. So depending on the structure, it's not evident whether, you know what I mean? That's why you probably do have a consensus with here, because the thing that's going to dictate whether it's the positive or negative is if this b squared minus 4ac is a positive or negative number. Of what root you're going to use. Well, obviously, if this is negative, you're going to have one root that's it's an imaginary. Both roots can be positive, you know, with 0 and time 2.14 or anything higher than 0. But yeah, that's just, I guess I don't know enough, but now I'm always going to have, anytime I do a square root, I'm going to have a positive and negative root. And I was going to show you one other way to simplify this. If we got some paper. Holy Toledo. And then we can be done. Alright, so one way to simplify this, we're going to go T max is equal to G plus or minus the square root of G squared plus 2GH divided by G. Because we did it reversed, what we can do is say, hey, is there a G squared here? Because if we have a squared term, I mean, you can do a lot of things, but the one thing that I'm going to show is we're going to have G plus or minus the square root, and we're going to factor out something that's double. I mean, not double, but like this. You know, if we can factor out a G squared, hell yeah. Then like this. Square root of this times something is the same thing as square root of that something times the square root of that. You know what I mean? And then if this just turns into G, hell yeah, it hopped outside of the square root. I think that's such a cool skill to have. So we're going to factor out a G squared. Now we're going to have 1 plus, but there is no G squared here. You know what I mean? So one way to represent that is like, well, throw in a G divided by G. If you can't see it yourself, do that, because now you'll have G squared up top and then a 1 divided and a G on the bottom. So this is 1 plus 2H divided by G. And now you got that divided by G. And again, you got T max is equal to G plus or minus. And now we'll just we'll do what we just said. G squared square root of 1 plus 2hg. So you have that, and then all divided by g. So this thing just becomes g, and this thing stays in the square root. And so we have g plus oh, this is going to drive me insane. Oh, no. Yeah, this plus or minus can still stay there. Like, I feel like I want to get rid of it till the very end. You know what I mean? Just guess what it is and then add it back in. But now we're good. So we have g plus or minus g, and then the square root of 1 plus 2hg, and then divided by g. So hell yeah. Now we can do g divided by g, and then this divided by g. So we have T max is equal to g divided by g plus or minus g divided by g square root 1 plus 2hg. You know what I mean? Doing every step at a time, these become 1, and you have T max is equal to 1 plus or minus the square root of 1 plus 2hg. And hell yeah, that's what we get. 1 plus or minus 1 plus 2h2g, and we know that from this the root is positive. 1 plus the square root of 1 plus 2hg. Hell yeah, so that's g max. And again, the problem asks for the distance between the 2 points, and we solved that right off the bat. That was d as a function of t is 2v initial cosine theta initial t, where t can be less than or equal to 0, but it can be, I mean, t is greater than or equal to 0, but less than or equal to t max. And then it can also be written like this: 1 plus the square root of 1 plus 2hg, and then hell yeah. So now this was my doing, is just like, well, if you have a table and a height with an h, and in this case h is a negative value. I would just put an asterisk there. In the setup, here's your origin, so h is a negative value. It's not the absolute value of h. And then g is negative 9.8. So those are the only two things that you would need to know. But then, with any height of any table, here would be your T max, so that's kind of a cool equation. And T max is only a function of gravity and the height. It's not a function of the angle. It's angle initial, it's not a function of that. Where this distance is a function of the angle initial, because it's like how far away things can go. You know what I mean? If you're trying to get that max because of gravity, 45 degrees gets you the max hang time and the max distance. You know what I mean? But yeah, so there you go. Hell yeah. Cool. So I guess we made this problem into a long one. It didn't need to be. But I'm glad we did. And the reason that I went on from there is because I just hand waved. I was just like, oh yeah, and if you made a table, you know what I mean? And I went to the position equation, and it didn't look right. Yeah, you would throw in a -2 here, and then I was like, yeah, how do you solve for t? And it still seemed like because I said if t is equal to 0, well, that's a root. But not to that equation. You know what I mean? The second you throw in a y value of negative h, like negative 1.5, no, you only have one value of t that makes sense. The other value is nonsensical compared to if you don't have that negative height and your equation just is this y is equal to, you know, acceleration divided by 2t squared plus the initial velocity in the x times t, then you can do that factor out of t. One of the roots will be 0, and then the other root will be the time that it takes to hit the horizontal. So if I said that right before I was ready to end the last video, you know, this video, then I would have just been, but I didn't understand that. So the second I don't understand something, hell yeah, I'm going to go back and explore it. And I don't know. I think I'll get better at like allowing you to come along for the ride. You know what I mean? Maybe, but no. I mean, it's just a good experimentation process of like, hey, do you want to see the learning process? Do you want me to go through problems where I'm gonna go through them until they make sense to me? If it doesn't make 100% sense, then I'm still just going to keep at it. And I can tell you where you hit the roadblocks. This one sucks. Anytime you do the quadratic equation, just expect tons of errors. It's like almost impossible not to make a sign error. And it's because you take A, B, and C, and typically one of these has to be a negative value. And then you have to throw it into like a -4AC scenario where you're just like, well, now what is this? Is it a positive? Is it, you know what I mean? So, and then there's so many little negatives. 1, 2, 3 negatives, and any of these things could be negative. And 1 is squared. So if B is negative, usually it probably won't be, maybe. But then it goes away once you square that negative value. So again, quadratic equation sucks, and just get the equation and then throw it into your calculator. Because that stuff that I'm working on, especially making these videos, is like, what is the backdoor shortcut to within, you know, like a minute, I can actually get an understanding of what's going on, so then I can move forward. And then if I do go through the math, get a wrong answer, I know it was just a sign error and not something fundamentally wrong with the axioms. So, hell yeah. Thanks for joining me, and that's a video.